suppose Haley at the first meeting said, I want to know how trig and imaginary numbers are used in electrical engineering. Something to that effect. So we're finally going to get around to that. Ish.
Still sitting here.
So we have, what we're talking about here are imaginary numbers. And imaginary numbers get their name, well actually, let's say it the other way around. Imaginary numbers give this letter its name. And this number is I. And I is what we call the square root of -1. If you think about it, that should not be possible. Because if you have the square root says what times itself equals the number here. And if it's a negative, sorry, if it's a positive number, then positive times positive equals a positive. Coincidentally, this would be 2, right? Because 2 times 2 is 4. 2 times itself is 4. However, it's plus or minus 2. Because if you have a negative number, and multiply by a negative number, it's also positive number, 4. But if you try to multiply a negative times a negative or positive times a positive, you get a positive number. And so this is impossible, theoretically. And we said, normally we would say, this is...
Cashley Queen to the front office, please. Cashley Queen to the front office.
We would say it's undefined. But then, we defined it. It's I.
We made up a definition.
We made up a number. So we said, what the heck, forget all you, we're going to define it, we call it I. Coincidentally, in electrical engineering, I stands for current, so instead they use the letter J.
Oh.
I think engineers' purpose in life is just to make mathematicians mad.
No, it's because power equals I times E.
Yes.
Pi.
Yep. So, and yeah, I stands for current. And so moving on, theoretically it's impossible to undefine, but we defined it because we're awesome.
Because we're human and we have to have an answer.
Yeah, I have to have an answer. So the cool thing about I is that, like we said, I squared should give us -1, right? So I to the first power equals itself. Yeah. And I squared equals -1, like we said earlier. So if we multiply that by I one more time, it would be -1 times I.
So it'd be negative I.
Negative I. And if we had I times I, negative I, rather.
I times negative I. That'd
you'd
be
have I times I, which is
-1.
times a negative, which is 1.
1, yeah.
And if you multiply that by I,
That's
you get
I.
I. So you get this pattern, and which leads to Miss Kramer's wonderful remix of Ice Ice Baby, or whatever Queen's song was that came way before it that he totally ripped off for that song, which is I'm -1, negative I 1, I'm -1, negative I 1, I'm -1, negative I 1, dun 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 dun. Yeah.
Yep.
So
This is Kramer.
imaginary. So,
Oh gosh.
oh, I should probably should have kept that up. Oh well, it's gone now. And the cool thing about that is that I -1, negative I 1, it has this repeating pattern of it's positive, I -1, negative I 1. It's I can't remember in my head without that.
Yeah.
So the cool thing is that it goes negative, negative, positive, positive, negative, negative, positive, positive. And so that's actually used in things like Taylor series.
Yay.
Ooh, pretty.
What?
Because it alternates every 2 instead of every 1, like, say, -1 to the power of n repeats negative, positive, negative, positive. Anyway, so that's used in series type things. And if you add a real number is what we call all numbers we normally deal with like 5 and 0.5 and 1/2, any of these real numbers, supposedly. Not because they're more real than imaginary numbers, but because we call it that.
Is it more real than imaginary?
So if we have 5 plus I, we call it a complex number, because mathematicians are really great at naming things.
Yeah.
Because it's complex, I guess.
Well, because, yeah, it's imaginary and real part.
Yeah. So we have, like Kim said, we have the real part, which is often called,
Oh, gosh. What is it?
it's called the REZ, which stands for real number. Normally, complex numbers are represented by a Z. And the imaginary Z. And where this gets cool is that you can represent any real number on a number line, right?
Mm-hmm.
Here you got 0, and here you've got the number of fingers on my hand, and here you've got how many times I've wondered why I'm doing this, and then here we've got my love for puppies. And anyway, you have all these numbers on this real line. And if you add a complex line, you get something even cooler. We're working in 3 dimensions, yo.
Three?
So if we were to do 2 dimensions. This is 1-dimensional on one plane, you're stuck. This is 2-dimensional. 2-dimensional thing. So if we have Z, we're trying to represent it, we go over 5 and up
1 eye.
which you can represent as either a point, or if you're asking for the, its magnitude, we use absolute value signs. Absolute value normally means distance away from 0,
Mm-hmm.
which is just, 5. But in this case, we're working in 3 dimensions.
2.
So it's just very small 3rd dimension. 2 dimensions,
It's
you're
the
right.
layer of ink that you can see.
It's
Invisible ink.
yes. It's 2 dimensions, so instead we're going to do Pythagorean theorem, it's going to be 5 and 1, and this is going to be rad 26. So the absolute value of this, or the magnitude, is rad 26. Anyway, the point of this being that you can show, this is called a vector, which all of you people who have watched Despicable Me know. Vector is a quantity with both direction and magnitude. Like my crimes, they have both direction and magnitude. Oh yeah, right?
That was impressive.
That was incredible.
That was extremely impressive.
And you can represent things by throwing pens. You can represent forces. Thank you, David. Thank you for that. So you can represent forces as vectors. So if you were, there's a force going in this direction, this hard, this much force, or this much, all sorts of different things you can do. Russ actually did a perfect example of this. If we were on a flat Earth,
Flatland.
if we were on a flat Earth and we were
So
saying,
back to 1870.
if we, here's our starting point, here's A, and here's B. We're trying to fly in a plane, and we're on a plane. Oh, 2-dimensional, never mind. Anyway, so we have our city that we want to get to, but there's unfortunately some air resistance pointing due south. So we're not actually going to shoot for here, because if we shoot here, we're going to end up down here. Then we're going to be in Los Angeles, and we're like, oh crap, Los Angeles, I hate Los Angeles. So, and then we're going to, so instead we're going to aim a little bit farther north, kind of like you throw up to aim to a basket.
Yeah, because of gravity.
Because of gravity. So we're going to aim this way. And if we know this distance, if we know, if we know this, actually this speed, if we know this speed or this distance, I forget which one it is, to be honest with you, because it's been a while. And we know how fast the wind is pushing, let's say 50 miles an hour, then we can solve for this third side. And we'll know how fast to go, or actually I think this is all distances. Yeah.
Yeah.
If it's 300 miles away and the wind is pushing you 50 miles out of your way, how long is this trip going to be? And thus how much gas do you need? And that sort of ideas.
Mm-hmm.
And that's a cool thing about vectors. Vectors can be represented all sorts of different ways.
Unless you don't see that.
You can, one of them is what we did here, Z equals
Well, then you
A,
follow the same angle that you take from B to A.
A
I
plus
think.
Going
BI.
faster now.
So this is one way you can represent
Well,
it.
I'm just thinking of-
Other people who have taken Tiller's class have probably seen a,
Was it U? Or?
I believe it's a vector I
Oh.
plus B times a vector J.
Oh, yeah,
And like I said, electrical engineers often use a J here instead. There's also one other cool way to do it, which is that this can be represented.
Hey Ben, you're gonna just shut the door when you're done.
Sounds good. Thank you.
Bye, guys.
This can be represented another way because of a fascinating quality of I, which is that E to the I theta equals cosine theta plus I sine theta. If you want me to prove this to you, I can, but I don't want to.
Do it.
yeah. That looks like a lot of work.
Do it.
I trust
Namely-
your math.
Do it.
This much work.
My goodness, okay.
So, this actually kind of makes sense because cosine is your x normally in trigonometry, and sine is your y. And you can also prove that because here's an angle. Here's your angle theta. Your opposite over hypotenuse is your sine, and your adjacent over hypotenuse is your cosine. And you just have to multiply by your magnitude for your scale vector. So this is cool because it represents everything in what's called a polar form, where you have your magnitude handy, and you have you have your theta, your angle rotation. So it's very easy to find out how to express your vector, because you just say, oh, you go this direction and you go that far, kind of like directions. Instead of saying, you're going to go exactly 25 miles this way and then 30 miles this way. Well, what about the roads? Don't worry about it, we'll get there. Instead, we're going to say, all right, turn this way and then go. That way.
You're in a helicopter.
So that's the
That's
benefit of
precisely
having
why.
this.
If you're in a helicopter, this is going to be helpful.
So that's the benefit of that. And however, what about this one again? What's the point of having this then? Because now you're just working in rectangular formats of this much over and this much up. And that just doesn't seem very efficient after this, which also has another hidden property, which I'll reveal at the end. But the cool thing about this is that you can rotate it really easy. Because what happens if you multiply this by I? Well, you're going to distribute A times I, not artificial intelligence, but AI.
And that'd be minus B.
Yeah, so
Because
I
I
times
squared.
I is going to give you -1. And then you're going to have your B still. So now it's going to switch places. It's going to be -B plus AI, which means you're now going down. You just flipped it, and you made it negative, which means you're going to actually rotate it 90 degrees. No one believe me?
I believe you.
Because that's going to, if you want to think of it this way, the rise over run is just been reciprocal, and it's negative now, so it's perpendicular.
Mhm.
So you've rotated it 90 degrees just by multiplying by I. And that's why vectors like this are super cool. Vectors like this show you go this far in this direction. Vectors like this are easy to manipulate and turn and twist. And forces, such as, I believe, I had trouble looking this up because it's way over my head, but electrical engineering, as well as other engineers, use these vectors to represent, like I said, forces in a direction, and can use I's to switch them, to switch directions. If you want to multiply this all by -1, you can flip it 180 degrees. If you want to flip it by, multiply by -I, you flip it 90 degrees in the other direction.
Huh.
So And all these things, you can manipulate forces and find out which direction, say, the current is heading, especially an alternating current, because it goes back and forth. So you want to be able to know how those things relate. And in fact, periodic functions show up all over the place when you start talking about alternating current, because you're going positive, negative. So that is the cool thing I find about vectors. And vectors can be expressed in I. The other one cool thing I will say about imaginary numbers has to do with what I just erased because I'm an idiot. So now I can write it big, in big letters.
Oh my.
E to the I theta equals, say it with me, class,
Cosine
theta
Theta.
plus,
Plus
please, make
I sine theta.
Yes. Magical.
Why?
Because let theta equal pi. It's understated because it's shy.
And impossible to read from the.
E to the I pi. Shall we do some substitution? Cosine
Oh, I think I get you.
plus I sine of pi. Trick kids, what's cosine of pi?
Who's a trick kid?
Negative 1.
I negative 1.
Trick kids, what's sine of pi?
0.
0, which means that I really doesn't matter anymore.
Yeah.
So, we'll do a little bit, that means e to the I pi equals negative 1, or the magical thing of it all, in what scientists are calling WTH, e to the I pi plus 1 equals 0. Here we have,
Jesus Spaghettis, please meet your right up front. Jesus Spaghettis, please meet your right up front.
here we have a number that expresses compound interest. Here we have the square root of negative 1, which shouldn't exist. We have pi, which is an arbitrary value of this diameter, the circumference divided by its diameter, which looks like a theta. Anyway, we have 1, which is our basic, most understanding basic number of all with unity. And we have 0, which is perhaps one of the biggest numbers we ever invented. All expressed in one thing, and how is that possible? Because math rocks.
That's awesome.